Hi, and welcome to our lecture on metabolism. Metabolism is basically all of the chemical reactions that occur within a cell and ultimately in a multicellular organism within an entire organism. But it sometimes also is talking about specific pathways. So, yes, it's all of the chemical reactions in our bodies, if you're thinking of humans, but these reactions oftentimes occur in what are referred to as pathways. So we're going to be taking a look at what's known as primary metabolism, which is the breakdown of glucose, and we'll look at a few different other processes that feed into it. But in order to understand metabolism as a pathway and how we derive energy from our foods and those sorts of things, we have to first understand proteins that are involved in this process, the class of proteins called enzymes. And we have to also discuss a little bit about energy. So let's take a look at some concepts in energy. So chemical reactions are governed by two specific factors. The direction of the reaction, you probably learned about this in chemistry. The direction of the reaction, so our reaction here would move from left to right. But we would also look at the rate of the reaction. So how quickly does this reaction from left to right occur, where A and B are the reactants, C and D are the products. Lowercase a and b in this particular reaction here are the concentrations or the molarity of each of these reactants. And of course, this will result in a molarity of our products, C and D. Now, rate is determined by things like input of energy, and that input of energy could be in the form of heat, or it could be in the form of light, or some kind of wavelength. It could be agitation, physical energy. There's different things that can alter the rate of a reaction. But in metabolism and in cellular processes, the number one factor that really determines or governs a chemical reaction is the absence or presence of an enzyme. And so enzymes are a class of proteins that are referred to as biocatalysts or biological catalysts. And these catalysts, to define a catalyst is something that is added to a reaction that will speed up the rate of the reaction. However, that catalyst will not be used up in the reaction. So when we go from A to B, we might add a catalyst here in the middle here somewhere, right? So we have A plus B plus a catalyst, an enzyme. That enzyme will make A and B come together and react more quickly. It does this by decreasing the amount of energy that we would have to put into it. This catalyst, at the end of the reaction, we have our products C and D. A and B were converted into C and D. However, our catalyst will now remain the same. So the catalyst does not get used in the reaction, and it does not become part of the reaction. It doesn't become a product. So that if we were to create this reaction a second time, the same catalyst could be used again. Now, this is important for enzymes because these enzymes need to be reusable. The cell wants to use these enzymes over and over again so they don't have to make too many of them. Many of our cellular chemical reactions have to occur in a large scale, meaning a lot of molecules. And proteins are expensive energy-wise. They cost a lot of ATP, a lot of energy to make. So if we want to make an enzyme that's going to make a reaction that has to happen all of the time, we need that enzyme to be reusable or recyclable so that we don't have to expend too much energy to make all of those enzymes. So when we talk about energy in the cell, we're really talking about the two basic forms, which are potential energy and kinetic energy. Now, kinetic energy is kind of the energy we associate with moving around. So that's your physical energy. It's also referred to as energy in motion or energy in action. So it's energy that's making something happen. Potential energy is energy that is stored. Now, it's sometimes referred to in physics. Potential energy is usually referred to based on location. So if you were standing at the top of a hill, you would have potential energy. You would release that energy, convert it into kinetic energy by rolling down the hill. So that location, by being at the top of the hill, you have that potential energy. If you were at the bottom of the hill, you wouldn't have that energy. You wouldn't be able to roll down the hill. In In cellular mechanics, in cellular, what we call energy kinetics, we look at potential energy in terms of chemical energy. And in this case, it's energy that's stored in the chemical bonds between two atoms in a molecule. So if we are to break atoms apart from each other, they release small amounts of energy. And that energy will be harnessed by the cell to do some sort of action. So our cells, many of our enzymes that we talked about in the last slide, these enzymes, their job is to break those chemical bonds, to break those covalent bonds between atoms in a single molecule in order to release the energy that they store so that the cell can carry out a particular process. So over here we have chemical energy. There's energy stored in all of these chemical bonds here. There's some type of energy. Double bonds store more energy than single bonds. Carbon bonds store more energy than carbon-hydrogen bonds. Carbon-oxygen bonds store more energy than carbon-carbon bonds. So different electronegativities of the atoms determine how much potential energy may be stored there. Regardless, this is here a sugar molecule. This sugar molecule is going to get broken apart, and every time we break one of these bonds, a small amount of energy is going to be released and be converted into kinetic energy. And that's what's happening here. This kid's able to hit a baseball with a baseball bat because he's using chemical energy in whatever foods and whatever chemical processes are going on in his cells to convert it into kinetic energy so that his muscles can move. So in metabolism, we're just taking these pathways of chemical reactions and transforming potential energy into kinetic energy. But that brings us to the concept of what's known as thermodynamics. Now, in thermodynamics, this is basically just the study of energy itself. And when we study energy, we always have to remember two very important laws, and they are slightly different. But I'm going to give you an analogy on these that might help you remember them. Now, first is the law of conservation. So in the law of conservation of energy, this states that energy cannot be created or destroyed, only transferred or transformed. So we can take potential energy and transform it into kinetic energy. We can take kinetic energy and transform it into potential energy. Think of water behind a dam, right? So hydroelectric power plants are water behind a dam. So the water, when it's behind the dam, is potential energy. When we open up the dam and allow the water to run through the dam, we put paddles in there, and those paddles get turned by the energy of the water moving, and that's going to create electricity. So the water behind the dam has potential energy. The water moving through the dam is kinetic energy. The paddles being rotated is kinetic energy, and the electricity being created becomes potential energy. That potential energy is going to run through wires and all of that to your house to make your vacuum cleaner run, which now turns it into kinetic energy. So we just constantly transfer energy from one form to another, from kinetic to potential and potential to kinetic. But one thing to remember is our second law. And in the second law of thermodynamics, during that transfer or transformation of energy, when we move energy from potential to kinetic or kinetic to potential, either way, during that transformation of energy, we get what's called an increase in entropy or degree of disorder. Now, what that really means is that when we transform energy from one form to another, let's say from potential to kinetic, when we transform energy from potential to kinetic, most of that energy is going to be harnessed for work, right? So we're going to transform that potential to kinetic energy to make something happen. However, some of that energy cannot be harnessed. It's going to be lost to the system. And by system, we just mean its environment or its surrounding. What we're really talking about is the universe. So the universe wants to be highly ordered, but as we increase entropy, the universe becomes more disordered. I know this sounds very ethereal, but here's a way to look at it. In our bodies, our cells are carrying out all of these chemical reactions. And every time we break down, let's say, a glucose molecule, every time we break down a glucose molecule, we are converting potential energy into kinetic energy. And every time a chemical bond in glucose is broken, potential energy in that bond is released as kinetic. And that kinetic energy will be used by the cell to do something. Every time we break all of these molecules, we use that energy. But some of that energy gets lost, and it gets lost to our bodies. And for our bodies, our energy gets lost in the form of heat. So our metabolism is what allows us to maintain our body temperature. Now, if I were to go outside and run around campus in the middle of the day, it's pretty warm outside. And the more energy, the more potential energy I convert into kinetic energy to make my muscles work harder, the more chemical bonds I am breaking. And the more chemical bonds I break, the more energy I release to the system, the higher my body temperature goes. So the more potential energy I convert to kinetic, the higher my temperature goes, because I am releasing or losing some of that kinetic energy in the form of heat. So that brings us to the idea of changing free energy. So free energy this is just a way that we calculate an energy transformation. Entropy is how much disorder cannot be harnessed to do work. So entropy is really that measurement of heat that's being lost when we're breaking down glucose. So total energy equals how much energy we can use plus how much unusable. So the total potential energy is how much is converted into kinetic, as well as how much gets lost to the system. Some energy is unusable, gets lost, and total energy is called enthalpy. So we have entropy, that's the energy that gets lost that we can't use. Enthalpy is total energy that we're trying to transform. So how much energy is being stored in that single carbon bond. Usable energy is the actual energy that gets harnessed to do work. So enthalpy is equal to usable energy plus unusable energy, or entropy. So you can see there are some terms here. We're going to show an equation. So that brings us to enthalpy equals free energy plus entropy, that's our S, and we multiply our entropy by temperature. Okay, so this is a measurement for energy. And in using algebra here, we want to find out how much energy is available for work. I want to know how much of that potential energy in a chemical bond I can use for work and how much is going to get lost. So this term is referred to as Gibbs free energy. Now, Gibbs free energy can be negative or it can be positive. And whether it's negative or positive determines if we have enough energy to do work. So we want to calculate what's known as Gibbs free energy. So for example, we want to determine if a reaction is going to be spontaneous. Now, by spontaneous, we are talking about the reaction occurring or moving forward without a massive input of energy. We don't want to put any extra energy into it. And if a reaction is considered spontaneous, when we calculate Gibbs free energy, we come up with a negative G. Now, spontaneous doesn't mean that the reaction is fast. It just simply means we don't have to put any energy into it. For example, let's say you want to cook a pot of pasta, a pot of spaghetti. You can leave spaghetti in the pot of water on your kitchen counter for a week. Eventually, because of energy that's already found in the water and it's at room temperature, so the water molecules are going to move, etc., eventually your water will cook the spaghetti. Eventually the spaghetti will become soft and be considered cooked and you could eat it. If you want to speed up this reaction, however, and you want to eat tonight and not next week, then you add energy to that system. You add heat to the system in order to speed up that reaction. So a spontaneous reaction will occur without any additional energy. If we want to speed it up, however, we can put some energy into it. But the key factor in a spontaneous reaction is what's called the free energy change. And this is where we come into our calculation. So delta G That's what this little triangle here means. Delta G means change in free energy. The change in free energy is equal to the change in enthalpy minus temperature times change in entropy. So let's see what this looks like in action. Delta G, if delta G is negative, then it's negative in free energy, then energy will be released. This is a spontaneous reaction. These are exergonic reactions, reactions in which you put two chemicals together and heat is given off or some kind of energy is given off. That's referred to as a spontaneous reaction. That's a negative free energy change. If a reaction is endergonic, then our delta G will be greater than 0. If it's greater than 0, then the positive free energy change, there's no addition of free energy, and it's not considered a spontaneous reaction. So in an endergonic reaction, our delta G is going to be greater than 0. And so here we have this positive change in free energy. We don't have to add any energy into the reaction to get it to occur. So this is referred to as a non-spontaneous reaction. If delta G equals 0, then there's no free energy either way, which means we're at equilibrium. So either at equilibrium or no reaction is going to occur. So here's our example, which is basically the breakdown of ATP. So ATP, adenosine triphosphate, is the primary energy molecule used in the cell for energy purposes. And what ATP does is ATP has these 3 phosphate groups. Whoops. Let's get my pen working again. ATP has these 3 phosphate groups right here that all have a fairly negative charge, pretty strong negative charge. And when we have to jam 3 negative charges up against each other like this, so closely together, this actually causes the storage of a really high amount of potential energy. And so these 3 phosphate groups have a lot of energy. And what ATP does, and we saw this in cell signaling when we talked about cell signaling, that phosphorylation, what ATP does is it drops off this phosphate group. So this is a free phosphate group. And when it does that, it's breaking this bond right here. And when it breaks that bond, there's a ton of energy in there. As a matter of fact, there are 7.3 kilocalories per mole of energy in this stored in this chemical bond here between the last phosphate and the oxygen on the middle phosphate group. This reaction is favorable to the formation of some kind of product. We want a delta G to be negative in order for our reaction to move to the right. We can use this energy to drive all kinds of processes. So I'm going to skip ahead to this slide here and we'll go back. So here I have glucose and phosphate, right? I need to get this phosphate onto glucose. So glucose plus phosphate gives me a glucose phosphate and H2O. This is one of the very first steps in the breakdown or in the metabolism of glucose. The first thing our cells are going to do is they're going to add a phosphate group to glucose. Now the delta G, the change in free energy required for this, is positive. I have to input 3.3 kilocalories of energy in order to add this phosphate to glucose. Where am I getting the phosphate? I'm going to get the phosphate from an ATP molecule. So I'm going to take that ATP molecule and I'm going to hydrolyze it. I'm going to add a water molecule. And this is going to give me an ADP, adenosine diphosphate, and a free phosphate. When I hydrolyze that phosphate group off of ATP and I create this free phosphate over here, I'm breaking that bond. Remember, I had these 3 phosphate groups that were bound to each other. So if I break this last bond here, I'm going to release 7.3 kilocalories of energy. I only need 3.3. So if I have a negative 7.3 and a positive 3.3, I have left over 4 kilocalories of energy. Those 4 kilocalories get released. In our case, this is energy being released It's an exergonic reaction. My energy gets released, and in our case, it's going to come off as heat. Our bodies will use this to maintain homeostasis. So let's go back. This hydrolysis of ATP, I'm going to go back one more, is the breaking of this phosphate group here. So this ATP molecule is going to donate this phosphate group and attach it. It's going to attach it to a glucose molecule. But it has to create a chemical bond to do that. That requires input of energy. It only requires 3.3, and by breaking this phosphate off, I get 7.3. So I have this leftover 4 kilocalories of energy that the body uses in terms of heat. So in that second law of thermodynamics, right, in our first law, I'm transforming potential energy to kinetic energy to potential energy. So I'm taking this potential energy, releasing it to create another chemical bond, that's the kinetic energy, and storing that energy, that 3.3, in that chemical bond on glucose. Now, those 4 kilocalories are left over, and that's the second law of thermodynamics. Those 4 kilocalories are now going to get released into the system. Now, in the hydrolysis of ATP, it's an endergonic reaction, and it gets coupled to a reaction that's exergonic. So it's a reaction that might require energy, but it gets coupled to one that releases. So when energy gets released from an exergonic reaction, it's used to, of course, move the endergonic forward. That's what we just saw with hydrolysis of, phosphorylation of glucose. An endergonic reaction can be spontaneous if the net free energy change is negative for both the endergonic and exergonic reaction. So that's what's going on here. We have this positive energy here, right? This is an endergonic, but it gets coupled to this negative free energy here. So our change in delta G, or Gibbs free energy, is what this delta G means, right? So that's delta G stands for Gibbs free energy. This Gibbs free energy is what allows our cells to transfer or utilize potential energy and transform it into